so it goes very clearly, rapidly to the bottom. Yeah. So you can see how this can generate fast flow speeds even in the deep ocean, which is normally a low energy environment. Okay? Yeah, it's pretty cool. Yeah. Okay. Just a quick demonstration of basically some of the physical processes that are responsible for the formation of some of the rocks we've seen both today and particularly on the first day. Okay, so first day at Crookdale Crag, we saw those turbidity or turbidite deposits, which were interpreted to have formed. Right. Yeah, just lay it down carefully. Yeah. Okay, so these are interpreted to have formed by fast-flowing water, but are deep marine. Okay, so that's kind of a little bit odd, because why would you have fast-flowing water in deep marine? So what I've got here is a tank that from a bin that I've stolen from the department to demonstrate some of these processes. So the first demonstration is all I've got is this is just water from a tap out the back. I've dyed some of this green, and what I'm going to do is I'm going to pour some of this water into the tank, okay, and we're going to see what happens. So I'm just using this sawn off plastic bottle so that I can pour the water into the shallow area and then kind of release it in one go. Okay, so I'm going to see what happens here. So hopefully you can see the water's just kind of spreading out a little bit, and it's kind of staying in the same kind of place. It's not really going anywhere. It's not really doing anything exciting. So what I'm going to do now is I've got here, and I think I've got some pre-mixed stuff here. I've just got some iron oxide powder. So I think it's magnetite. It's available from Amazon if you really want it. So what this is going to do is this is going to give us a suspension of particles in that same water. Okay, so the particles should sink through the water, right, because they're more dense than the water, because magnetite's quite a dense mineral. We're all happy with that kind of concept. So what I'm going to do is I'm going to add my black magnetite, it's kind of all dewy and black, to this. Where's my thing on? Kind of give it a stir up. Hopefully, just leave that there so I can stay. So I can grab it later. So hopefully what you'll see is that it'll be acting slightly differently now. If I pour that in, you can see that the mixture is not behaving the same. It's starting to move down the slope. Okay, and it's moving down the slope quite quickly. It's almost made it to the bottom, and this is because the suspension of particles in the liquid are not acting kind of like separate particles in a fluid. The mixture is acting as one. Okay, so the packet of water at the top kind of mixed together with the iron particles was overall more dense than the water surrounding it. So that meant it started to sink down through the. So we'll just have another go doing that with these, and you can see that it starts to career off down the slope. Okay, so this is analogous to on a continental margin. Okay, so you might have a storm that happens in the continental shelf somewhere that might mix up a bunch of sediment on the continental shelf, and if that moves to the slope, it'll start flowing downhill. And in this example, we've just got a plastic bottom to the bin. Okay, so no extra sediment's going to be added. But we saw on the first day, okay, that there was evidence of erosion along those flute casts. Everyone see those? So as the flow moves down the hill, it's constantly eroding sediment, which adds sediment to that packet of water, which makes it more dense, so the flow speeds up. Okay, so you can get these flows going very, very fast down the continental margin. Okay, so this is the same phenomenon that I showed you in the video with volcanic plumes. In that case, it was just a mixture of rock and gas was denser than the atmosphere around it, causing it to basically fall down through the atmosphere rather than rise up, forming these pyroclastic density cones. Okay, so that's one observation. And it'll become clearer when I do it with this powder later on, and this is calcium carbonate. So it's less dense, but it's easier to see in the water than the dye. Yeah, turns out green dye is not a very good dye to use. So the next experiment is to look at what might happen to explain some of these really fine laminations that we saw at the last stop today. So one of the hypotheses is that all they are is the very, very distal manifestation of this process. So this thing trundles down the continental slope, it gets onto the flat abyssal plain of the ocean, okay? And eventually these things kind of gradually slow down, and then the sediment gradually falls out in these very fine layers, maybe hundreds of kilometres away from the original source. So that's one possible route the sediment could be taking. So each of those tiny laminations could be one of these currents that's happened hundreds of kilometres away, and sediment just gradually kind of falls out. Now, an alternative is that actually the sediment can be transported from the coastal region to the open ocean in a different mechanism. So it doesn't have to go along the bottom, it could go along the top of the ocean. So some of you might have done oceanography course this term, some of you not so much. It doesn't matter, but the ocean has effectively got two layers. There's the deep ocean, which is cold, okay, and then the surface ocean, which is quite warm. It's a layer of maybe only 100 metres thick, but because it's warm, it's buoyant, it's less dense, so it sits on the top of the ocean. It also, in some cases, can be less salty. So if you've got lots of rivers going into the ocean, you could have a layer of buoyant water on top of the salty ocean. And we're going to simulate that with hot water. Okay, so that's like having fresh water on top of salty water, but well, I'm not going to fill this thing with salt and then kill all the plants when I empty it. So I'm just going to gradually, hopefully, fill the surface of this with hot water. So some of you might be able to see a layer of water forming on the surface where we've got, yeah, so because the refractive index of hot water is less than that of cold water, or at least different. I'm going to confidently say it's less, but oh, there we go. Put another one in just for. So now I've got what is effectively a stratified ocean. So I've got a warm layer on top of a cold layer. Does that kind of look set?
Yes.
Okay, right. So now what I'm going to do is I'm going to simulate what would happen if we mixed some sediment in with some fresh water. So the water's buoyant, but the sediment's heavy. I'm going to see what's going to happen there. So I'm going to add some hot water. Hopefully this is hot. Yeah, it's kind of hot. And I'm going to mix in now some of the lovely white powder, which I promise is just calcium carbonate. So this should eventually settle out to the bottom. Oh. There we go. That in there. So you can see that some of the water kind of went down, but hopefully you should see it starting to spread out along the surface in some places. Is it?
Yeah, at the front it is.
Yeah, and then settling out. Okay, so this would be faster if there was some wind and waves. Wind and waves spreading out the surface water. Well, it's kind of interesting. You can see it's also coming out at a kind of a layer of neutral density. So it's not necessarily going out along the surface. Okay, you can see how I've started mixing. So the surface ocean is blown around quite a lot by the winds, whereas the deep ocean is not. Okay. So you can see now that this water has got, so this surface layer has got out into the deep ocean. So potentially some of these laminations we're seeing in our sediment, those could be plumes of water that are coming from a river somewhere, adding sediment and fresh water to the ocean, and that's being taken out quite a long way by this it's called hyperpycnal flow. I mean, the exact meaning of that doesn't really matter, but it's basically a layer of buoyant water that's spreading out along the surface of the ocean, containing some sediment, and then that would sediment would eventually settle out for the ocean. Okay, so you can kind of see how you might develop layers of sediment in our rocks by a process like this, by adding surface water, so adding river water near the margin, and that spreading out across the surface of the ocean, but still taking sediment with it. Okay, so the sediment doesn't have to drop out straight away. Okay, so I'll do one more, but this time with the cold water and the white stuff. So you can see the turbidity current. I had a spoon. Ah. So hopefully with this one you should be able to see the water go very clearly. So this is the cold water, so it goes very clearly, rapidly to the bottom. Yeah. So you can see how this can generate fast flow speeds even in the deep ocean, which is normally a low energy environment. Okay? Yeah, that's pretty cool. Yeah. Okay. Right, so just wanted to show you that because now we can kind of start to link some of the physical processes in the ocean and in rivers and stuff with the rocks that we're seeing in the field. Okay? So I guess dinner is at past again, and then after dinner we're going to go over some of the observations from all today and prep you for your mapping. So it might be a little bit of a long day, and you might have to bear with me because Kate was supposed to do it and I'm going to have to learn it. So